So for, what, over 50 years now, the entire digital world has been built on a single, really elegant rule.
Yeah.
Binary logic.
Right. 1 or 0,
Like,
on or off.
it's the foundation of everything, every computer, every server, every single cloud instance you touch.
But that simple elegance is now slamming headfirst into a wall of physics. We rely on electrical switching, right? The silicon transistor.
Of course.
And that process, fundamentally, it generates heat. As we make these devices smaller and smaller, the heat density just skyrockets.
Creating what the sources are calling the heat wall.
Exactly. And it's an unavoidable constraint. You can't scale it further without either melting the chip or using an absurd amount of energy for cooling.
So it's a hard ceiling, a physical stop for any electrical strategy. It basically tells us that the binary system, or at least how we've built it electrically, has run out of road.
It has. So our mission for this deep dive is to look at sources that are detailing a pretty radical shift. It's about jumping domains entirely. We're looking at a new magnetic architecture. It's called FluxWorx, and it promises stable multi-valued logic, or MVL, and it can scale where silicon just can't.
So the core idea for you listening is that this isn't just a hardware upgrade. It's not about faster clock speeds. This challenges the absolute dominance of binary.
It forces us to ask a really fundamental question.
Which is?
If we were starting computing from scratch today, with everything we know now, would we still choose base 2?
That's a great place to start. Why did we stick with binary if it wasn't, the best possible choice?
It's all about historical inheritance. Binary logic wasn't adopted because it was mathematically superior. It was adopted because the first computers, the electromechanical relays, they only had 2 stable states. They were either conducting or they were not.
So the hardware literally dictated the software? The logic was just baked in from the very beginning.
Precisely. And when the transistor came along, it solved the speed and the size problem, but the logic, that 2-state system, it just got carried right over.
And the whole ecosystem just grew up around it.
The entire thing. All the software, the compilers, the manufacturing, everything just crystallized around this dualistic worldview. It became the default, but it was never destiny.
And the sources are really clear that people knew this wasn't optimal for decades. We've been exploring multi-valued logic for a long, long time.
Oh, yeah.
The famous example is the Soviet Cetin computer, right? Based on ternary, base 3 logic, from all the way back in 1958.
Cetin is such a great example. It proved ternary logic could work, that it had these clear theoretical advantages in efficiency. But then the world shifted to solid-state silicon.
And trying to implement MVL on silicon became a
complete nightmare. And the heart of that nightmare was voltage stability.
Right.
If you're using voltage in a transistor, you have to divide your range, let's say 0 to 1 volt, into multiple distinct levels. For ternary, you need 3: low, medium, and high.
And I'm guessing that medium state is the problem.
It's the absolute failure point. Think about trying to set a dimmer switch perfectly in the middle, between on and off. Now imagine doing that millions of times a second on a device that's tiny, hot, and constantly being hit with electrical noise. It just drifts.
So the intermediate states were just too fragile.
Completely fragile. You had tiny noise margins, thermal drift, leakage. All these fluctuations caused error rates that were just way too high for any commercial use. It was dense in theory, but useless in practice.
So the electrical domain itself, the physics of it, defeated the whole multi-state idea. We needed a system where the states were just inherently stable.
Yes. And that brings us directly to the breakthrough described in the FluxWorx sources.
So how do they solve it?
They solved the stability problem by shifting the entire domain of computation. They've developed this patent-pending magnetic transistor and architecture. It operates completely outside the weaknesses of the electrical domain.
Outside of charge carriers. So wait, what's the new logic element then? What are we switching instead of voltage?
We're replacing that resistive charge carrier switching with something called field domain switching. They use magnetic domain gating. So instead of trying to hold a very precise voltage level, you're defining your logic state by the direction of a stable magnetic field.
Like the polarity of a tiny compass needle.
That's a fantastic analogy. A magnetic state is intrinsic. It's either north or south, or maybe east or west, but it is a distinct physical condition. A voltage is just an actively maintained potential.
It feels more robust.
It is. Think about it. It takes energy to flip the polarity of a little magnet, but once it's flipped, it holds that state. It's stable even if the temperature fluctuates a bit. This gives you incredibly high contrast between states.
Unlike electrical MVL, which is trying to maintain this fuzzy, unstable potential in the middle.
Exactly.
So stability is baked into the physics. But what are the trade-offs? I mean, if this is so much better, why aren't we already making magnetic logic chips everywhere? Is it slower? Harder to manufacture?
That's the key commercial question, right? And the sources do acknowledge that, yes, early magnetic logic technologies had some speed issues compared to silicon, but FluxWorx's architecture is specifically designed to be highly compatible with existing manufacturing processes.
So it's not a complete teardown of the fabs.
Right. And while the switching speed of one magnetic gate might be a little different from a silicon transistor, the ability to pack twice the information onto every single signal line, well, that often makes the overall computation much, much faster.
Ah, so the density gain makes up for any potential lag in raw frequency. And that brings us to the real consequence of this stability. We finally have a rock-solid foundation for MVL.
We do. And the stability allows them to reliably support not just binary, but ternary, quaternary, and even higher-order multi-state logic systems.
Okay, let's pivot to that density aspect, because this is crucial, beyond just heat. We're always hearing about the interconnect bottleneck in modern chips.
That bottleneck is everything. Modern chips are often limited not by the number of transistors we can fit on them, we are ridiculously good at that, but by the sheer physical number of metal wires, the interconnects, needed to move information around.
It's a traffic jam.
It's a massive traffic jam. You can generate the data, but you can't move it through the highway system fast enough.
So this is where MVL comes in.
This is where it provides huge architectural leverage. A binary logic system carries 1 bit of information per wire. 1 bit. But if you can give that wire multiple stable states, that single wire suddenly becomes exponentially more valuable.
Okay, so walk us through the math on that. What's the actual density gain?
With ternary logic, base 3, a single wire carries about 1.58 bits of information per signal.
More than 50% extra capacity.
Exactly. Now jump to quaternary logic, base 4. You are carrying exactly 2 bits per signal unit.
You've doubled your information throughput, double the density.
Without adding a single extra physical wire. You are, to use your analogy, adding a second lane to the highway by just changing the logic of the signal, not by rebuilding the road.
That is leveraging physics in such a smart way.
Mm-hmm.
But let's get into the theoretical side of this, because the sources mention radix economy. I hear base 3 is somehow optimal. Why? Why isn't base 4 or base 8 even better?
This is one of my favorite parts. So radix economy, it's a measure of the overall cost to represent numbers, the complexity, the hardware, how many digits you need.
The efficiency of the numbering system itself.
Precisely. And mathematically, if you look at the continuous ideal base, the most efficient base possible is the constant e.
The natural logarithm base, like 2.718.
That's the one. And since we have to use a whole number for our logic states, you can't have 2.7 states, we just look for the nearest integer.
Which is 3.
Which is 3. Ternary is mathematically proven to be the most efficient discrete numbering system known. Binary was just an inherited constraint, not the optimal choice.
So the math has always preferred base 3, but it's only now, more than 60 years after the Sutton computer, that we have reliable hardware to actually do it commercially.
That's the breakthrough. Now, while base 3 is the most efficient, base 4 is only slightly less so, and it has a huge architectural advantage.
Which is?
It aligns perfectly with binary. 4 is 2 squared, so a base 4 state represents exactly 2 binary bits. That makes it incredibly friendly for integration for compilers.
It's an easier bridge from our current world.
A much easier bridge, which is why the sources suggest base 4 could be the immediate practical target for implementation.
And this change doesn't just help move data around, it actually streamlines the arithmetic itself.
Oh, dramatically.
Yeah.
Multi-state logic compresses operations. Because a base 4 state processes the equivalent of 2 binary bits at once, complex operations like high-precision arithmetic become, well, shallower.
Shallower.
Fewer steps. Imagine adding 2 huge numbers in binary. The carryover, the ripple carry, can take many, many steps. In a base 4 system, you're resolving twice as many bits in each of those steps.
So fewer steps means faster computation.
Much faster. Especially for anything heavy on arithmetic like AI matrix multiplication. It's a compounding advantage. First the density gain, then the arithmetic efficiency.
And it all comes back to the physics of reliability.
Mm-hmm.
We failed with electrical MVL because of leakage and drift.
But magnetic domain gating gives you these distinct high-contrast states based on stable magnetic fields. It just eliminates those electrical error mechanisms.
So no voltage drift, lower thermal sensitivity.
Yeah.
You're getting the high reliability of binary, but with the density of MVL.
That's the goal,
So
yes.
how does this get us past the heat wall? That was the problem we started with.
Right, so this gets us closer to the theoretical minimum for energy usage. Electrical switching has to dissipate heat. It's fundamental. You are passing current through resistance to define a state. You're heating a tiny wire every single time you switch.
We're literally turning half our computing power into waste heat.
Pretty much. But by regulating states with magnetism, with stable fields instead of resistive transitions, the architecture moves toward what's called conservative logic. You're not actively burning energy to hold a state in the same way.
So the energy cost per operation just plummets,
It drops dramatically. It moves us much closer to the absolute theoretical minimum energy for computation, the Landauer limit.
which means cooler chips, which means we can pack them tighter. It solves the heat wall problem by sidestepping it entirely.
And that leads to the ultimate advantage, scaling. We know silicon gets leakier, hotter, and less reliable as it shrinks. The roadmap is almost at an end.
But what happens when you shrink magnetic logic?
It gets better.
It gets better.
It becomes more stable, not less, as the dimensions shrink. It avoids every single crisis that's killing silicon. There's no leakage explosion, no thermal runaway, and crucially, no electromigration.
Which is the physical movement of the metal atoms from the current.
Exactly. But you're not pushing nearly as much current. This opens up a whole new scaling frontier that electrical logic, with its binary inheritance and heat limits, simply can't reach. This isn't just an improvement. It's a new computational primitive.
So let's sum this up for everyone listening. We've looked at sources detailing a logic family that's cooler, has higher information density, is more stable, and has way more efficient arithmetic. It's a real path beyond the limits we inherited with binary. The heat wall was a problem for the electrical domain.
But it's a non-issue in the magnetic domain. It forces you to realize that the constraints we always thought were fundamental to computing, speed, heat, density, they were really just constraints of the material we chose 70 years ago. We were just working in the wrong physical domain.
Which brings us to a final, provocative thought for you to take away. If the most efficient numbering system known to science is base 3, and we now have the reliable hardware for it, what's next? The hardware problem seems to be on its way to being solved, but the infrastructure challenge, that's a whole other story.
Think about how deep that shift goes. We're not just rewriting some software, we have to reconceptualize it. We're talking about restructuring instruction set architectures, redefining data formats, building new compilers and operating systems, all designed for a ternary or quaternary world where the smallest unit of information isn't a single bit anymore.
That monumental software challenge, that's the real leap now.
That's the leap we have to make if we want to finally adopt the optimal system that physics seems to have preferred all along.
A deep dive into a truly revolutionary shift. Thanks for joining us. We'll see you next time.